Namaste everyone. Mrs. Mohan here. I'm back again with the continuation of the previous lecture. If you had watched the video, we stopped with the discussion on solenoid. So we will be continuing with it today. So if you remember what we talked about a solenoid in the previous class, you remember that we wrote a solenoid is insulated copper wire wound on a non-conducting cylinder, right? This is what we talked about as a solenoid, right? A solenoid uh, behaves as an electromagnet because when current passes through any wire, any conducting wire, particularly a copper wire, magnetic field is produced around it. We discussed this in the previous class. So we will be discussing solenoid and electromagnets in detail today. So I'm going to actually start talking about the solenoid today. Here is a video for you. So if you look at this video, you see that there is a bar magnet with the magnetic field lines shown on the right hand side, and you see a ring. So let us consider this ring as a circular coil of circular term of a conductor. Is that clear? We saw this also, and we did about the right hand grip rule, the clock rule, in order to determine if current is going to flow through this conductor and if magnetic field is going to be produced around it, what will be the direction of the magnetic field. So let's see what happens over here, right? So I am going to consider this particular ring, right, which is a conductor. So what happens when current flows through it? You can see the magnetic field lines that are drawn, right? Now what are we going to say at every point, right? We can either apply the right hand thumb rule or the right hand grip rule, right? So how is the right hand thumb rule applied? For both the cases, you need to know what is going to be the direction of the current flowing through the conductor. So in this case, the current is considered to be in the anti-clockwise direction. You can see this tiny blue arrow, the tiny blue arrow that is over here, which is showing the direction of the current, right? So when I am going to hold the grip rule pattern, you can see that the thumb shows the direction of the magnetic field, which is in the upward direction. So you can see the magnetic field lines moving up, and at the corners you can see the circular pattern, and at the center you can see the straight pattern that are going to move. Now if you look at this pattern that is going to be here and the bar magnet that is here, you can see that there is a slight difference, because if you look at the bar magnet is slightly longer and the field lines are longer. Whereas if I'm going to come and look at the ring, you can see that the field lines are shorter. Actually, it is a very small space over here. So what should I do in order that I need to elongate the magnetic field lines so that it is going to resemble that of a bar magnet? Because I have said that when current is going to flow through a solenoid, it is going to behave like a bar magnet. So what can I do in order that I can achieve this? So what are we going to do? We are simply going to introduce another ring parallel to it and below it. Now look at it. What have we done? We have actually brought in another ring over here, through which again current is going to flow in the clockwise direction. But again, what do we know? This ring is a separate ring. It will have its own magnetic field, which will have its own magnetic field lines. So if I am going to imagine the magnetic field lines of just below your first ring, how will the magnetic field lines be? So do you see, we have shown it using a different color here. You see that these magnetic field lines are its own. That is the magnetic field lines of the ring that is below this. But what is the most important property of magnetic field lines that we know? Can you imagine field lines crossing each other, touching each other? No, because we know that magnetic field lines never intersect. So what is going to happen? These two magnetic fields are going to interact among themselves, and they are going to space themselves in such a way that you are going to have a new magnetic field pattern. Can you see it, children? So beautiful. You have the magnetic field pattern of the ring above in its own way. On the below ring, you have it in its own way. But because they cannot intersect with each other, you can see that they are almost straight in this ring, they are almost straight in this ring, but slightly curved in between. But we don't want that curve also. Do you see in the bar magnet, there is no curve anywhere. So what are we going to do? You know that obviously now, right? So what am I going to do? I am going to introduce a third ring in between the two rings. But sorry, but once I'm going to introduce the third ring, you know again that this third ring has the magnetic field lines of its own. And again, we are going to defend saying that magnetic field lines cannot intersect with each other. So what is going to happen, children? These lines are going to have a mutual understanding among themselves. They are going to space apart, and they are going to arrange themselves in such a way. You can see this beautiful pattern that is being formed on the screen right now, right? You can see that they are almost straight now. Do you see that, children? Almost straight, but for the few wriggly shapes here and there. So now just pause the video and tell me, in order that I straighten up everything, what am I supposed to do? Introduce as many rings as possible long copper wire, and I am going to wind it, so each other, forming n number of turns. That in between those turns, if my magnetic field is going to be set up, it is going to exactly resemble my bar magnet. Do you see in the picture, children? You are going to introduce ring after ring after ring. That is, I am eventually going to form a coil of wire which is wound in the form of a cylindrical tube. So effectively, what do I get? Do you see the transformation? So wonderful. What is the transformation here? Do you see that this structure, which is actually loops of wire, has transformed into the magnetic field pattern of a bar magnet? So this can happen. Please remember this very carefully. A solenoid does not behave as a bar magnet, while a current carrying solenoid will behave as a bar magnet. So you can see that the pattern has become exactly similar to that of a bar magnet, and such a setup where you have copper wire wound in the form of a cylindrical tube is what we call as a solenoid, right? A solenoid means a tube, a pipe, a wound pipe with the help of copper wire. And remember, it has to be insulated copper wire. Is that clear, children? So I'm going to go back and write on the board that you saw now what happens and how we are achieving a bar magnet pattern in a solenoid. So we are going to say a current carrying solenoid, please understand, behaves as a bar magnet. It behaves as a bar magnet. So a bar magnet means it has to have its north pole and the south pole. So I'm going to, let's go over here and look at a solenoid once again. You remember I shared this with you in the previous class also. So do you see that we have coils of wire turned around, n number of turns, and you form a cylindrical tube. And if you are going to make the core into a non-conducting material and connect the ends of the copper wire to a direct current source. I apologize, in the previous class I was continuously saying DC current, AC current. Actually DC का मतलब ही direct current है और AC means alternating current. So there is no point in me saying DC current source. It's basically a DC source. That means it is a direct current source. Beautiful example is your battery, right? And you're in those batteries basically are sources of direct current. So when this solenoid is going to be connected to a direct current source, it's going to behave like a bar magnet. You can see this structure here now, magnetic field lines around a current carrying conductor. If such a question is asked in your paper, make sure that you have to show the polarities of your battery. Don't forget to do that, right? You are going to show the polarity of the battery, and you are going to show, you can see here, you can see the polarity of the battery over here, and you can see the polarity of the magnet magnet. How are you going to decide? For that, we are going to use our clock rule. Remember, children, we saw a rule called clock rule in our previous class. If you remember, we drew two circles. I'm going to just brush it up because without that, we wouldn't be able to understand the negative and positive of our solenoid. So let me go into this, and I am going to pick up my pen and put an S. I hope you are remembering now once you saw the picture. So I'm going to put the arrow mark. So following that arrow mark, I'm putting an arrow mark on the circle also. So following the same arrow mark, if I put this, so what did this law say, children? From the side that you are viewing a circular coil, if current is going to flow in the clockwise direction, then that pole that you are facing will be the south pole. And from the side that you are facing the circular coil, if the direction of the current is anti-clockwise, that means that pole will be your north pole. Now I'm going to share the picture of your solenoid again with you. Look at this solenoid very carefully, right? Do you see that current is moving from here now? View that part of the solenoid and move your finger in the direction of the current. Look at the way your finger is moving. Your finger is moving clockwise. That means current is flowing in the clockwise direction. So what will be that pole? That pole will be south pole. Now do not change the direction. Now turn yourself and look at the other side of the coil, that is this side of the coil. How is the finger is circling? It is moving in the anti-clockwise direction. Pause it again. I'm telling you, pause it again. See how your finger is moving on both sides. And you can do one more wonderful thing. Redraw this circuit diagram in your notebook and change the polarity of the battery. What will happen, children? What will happen when the positive of the battery comes to your left hand side? Your current will start moving in the clockwise direction from this side. So what will happen? That pole which is north in this picture will become south. That's the beauty of electromagnet. You can change the poles of an electromagnet simply by doing what? By reversing the direction of the current. That's something wonderful about electromagnet. Can you imagine, children? You can change the poles of the magnet, which you cannot do in a bar magnet or in a horseshoe magnet. When it is north, it's fixed north. When it is south, it's fixed south. Whereas in an electromagnet, if it is north, under one case of the current flow, if you reverse the current flow, the direction of the current will change. Is that clear? Now, ye jo jagah hai, this region in between the solenoid, I will show you the picture of the solenoid over here. This region within the solenoid, if it is left empty, we call it as a solenoid with an air core. I'm going to call it as a solenoid with an air core. Yes, obviously it is going to behave like a magnet. There is no doubt about it. But if I am going to, I stopped the share. I'm very sorry about it. I'm moving into the video now. If I am going to introduce a core, which is a soft iron piece, right? Soft iron का मतलब ये नहीं कि वो soft है. It is soft that it is soft like sodium metal or something. Is that clear? The meaning of soft iron is it's a type of iron. That's for you to think deeper. We have wrought iron, we have pig iron, we have soft iron, we have hard iron. Everything is solid, which is not soft. Okay. Now, soft iron, the amazing property of soft iron is it will get magnetized very easily. And at the same time, it will get demagnetized also very easily. That means the moment you are going to introduce the soft iron into the core. What is core, children? I told you what is the core. The space in between the coil is what we call as a core. If I'm going to introduce a soft iron in the magnetic field, soft iron gets magnetized. So the magnetic field of the soft iron gets added to the magnetic field of the solenoid, increasing the strength of the solenoid as a magnet. So what does a soft iron core do? A soft iron core increases the magnetic field strength. Whereas in the place of a soft iron, if I'm going to use a hard iron, then it takes a long time to get magnetized. Not only that, once it gets magnetized, to demagnetize also is very difficult. So hard iron, where do we use? We use hard iron to form permanent magnets, while soft iron is used to form temporary magnets, that is electromagnets. So if I am going to introduce a soft iron core, the strength of the magnet will increase. What else can increase the number of field lines, children? Can you guess? Pause the video again for a moment. And can you guess what else can increase the magnetic field that is formed by a current carrying solenoid? I have to simply increase the number of lines, right? So number of lines can be increased in two ways. Number one, what if I increase the number of rings? The number of lines will increase. So that means if I increase the number of turns, the field strength will increase. And number two, what if I send a very strong current? Greater the current, greater the magnetic field. So I'm going to put this onto the board and you are going to remember it very, very carefully. What am I going to do in order to increase the field strength of a current carrying solenoid? How am I going to increase it? I can increase it in three different ways. Number one, what can I do? By increasing the number of turns of the coil. Very right. And number 2, what? By increasing the strength of the current flowing through the coil. You are absolutely right again. And what is the third thing that we are going to say, children? The third thing that we are going to say is by introducing a soft iron core, I can increase the magnetic field strength of a current carrying solenoid. What is a current carrying solenoid otherwise called? It is called as a temporary magnet or an electromagnet. Now what am I going to do is this. I am going to draw a table and I'm going to put down the differences between electromagnets and permanent magnets, right? What is the difference between electromagnets? So one side I am going to put electromagnets and the other side I am going to put temporary magnets, right? So what are we going to put it under here? What are all the properties of electromagnets? Let's first put permanent. I'm sorry, I made a mistake. This is not temporary because electromagnets are temporary magnets, right? So these are basically permanent magnets. Yeah, so let's first put down the points under permanent magnets. Permanent magnets, the magnetic field strength is constant, children. Are you clear about that? You cannot change it. The poles are fixed. The strength, what else can we say? The poles are fixed. The magnetic field strength is constant. It cannot be varied. And they generally possess weak magnetic fields. And then what else can we say? They are of fixed shapes and sizes. Too big you cannot expect in permanent magnets, right? And then most important, once they are demagnetized, they cannot regain their magnetic properties. That means you cannot magnetize and demagnetize them at your own will and wish. Whereas if I come to electromagnets, what all are we going to talk about electromagnets? So beautiful. The magnetic field strength can be varied. How can you vary it? Go back to the previous page. How did we vary it? We varied it by 3 different cases. Isn't it, children? By varying the number of turns, by varying the strength of the current, and by introducing a soft iron core. So that means I can vary the strength of the magnetic field of an electromagnet. The poles can be reversed by, how can I reverse, children? By reversing the direction of the current flowing through the magnet, right? You can reverse the direction. And what else are we going to say? The field generated is strong than the permanent magnets. That's why when you are seeing cranes that are lifting very heavy objects, they generally use electromagnets because the strength can be increased multifold by increasing the current that is flowing through it or by increasing the number of turns. And then they can be designed in various shapes, and sizes. There is no restriction. And then they can be magnetized and demagnetized by how? Switching on and off the current through them. Beautiful, isn't it, children? Right? So I can switch on and off the current that is flowing through the electromagnet and either magnetize it or demagnetize. The moment you switch off the current, there is no more field, so it is demagnetized. The moment you pass the current, it is magnetized. So we saw a wonderful video talking about how a solenoid behaves like a bar magnet and how is it achieved, and we saw the differences between electromagnets and permanent magnets. So part of your lesson is over. So I will meet you again on Thursday. Make sure I'm going to see you again on Thursday with another video lecture. In the meantime, I'm going to send you one interesting quiz which you are going to attempt and keep your answers ready, because I will be giving you the verifying answers during my next class on Thursday. Till then, keep studying and stay safe. Thank you, children.